This conference will now be recorded. Okay, I guess we are starting. Welcome to the October edition of the EDGE project. Just for a little clarification, I'm sure it's well distributed now, but this project sub-project is no longer OpenEdge, as OpenEdge applies a single form factor that was contributed and has been adopted by several members. But now this is renamed EDGE, which really kind of opens it up for additional form factors, additional concepts, and really allows it to do much more than it would be able to do by limiting itself to just a single implementation. And so with that, Howie, I think you're the presenter now, but let me take over for just a second.
Yeah, of course. Go ahead.
Because I would like to start off with just a couple of bookkeeping items. If I can get it open. Here you go. Hope you can all see what I'm showing. No, I don't want to do that. So starting off, we are going to have the OCP Tech Week coming up. It's on November 9th through the 13th. Unfortunately, due to these times, we can't all meet face to face like I know we'd all like to do, but it is a information-packed 4 days. But the one thing I do want to focus on is the presentations from the telco and edge track. It's going to be really full. We apologize for those that we were not able to fit into this into this presentation day. If you have any presentations that if unfortunately you received a decline, and you would like to present them, this forum is open for you to present. So please contact me at any point that you would like to give your presentation, and I'll make all the time available that you need. And so going down the list, we kind of divided it into it's a morning session and an evening session. The morning session steers a little more toward Europe and the US, and then the evening session is allows our colleagues in the Pacific Rim area to really participate as well. So we do have certainly a full morning that's a little more open edge focused, some new contributions, some new some new types of deployments that will be listed. We're going to have a panel session on distributed edge cloud, which I think is going to be very interesting. Some of the repurposing and extending OCP designs for open edge. I certainly look forward to that. And then we're going to take a break at noon and not pick up until 5:30 in the evening. Now 5:30 in the evening a little better aligns us with the with the Pacific Rim, and on that we'll have some deployment discussions. Howie, you're going to preview your presentation for us here in a few minutes. That'll be then, and then we'll have a little more of a 5G focus with a few presentations focusing on 5G, and I'm very much looking forward to this entire day. In addition to that, the one other thing I did want to show you was these contributions. There are several of them that are out for voting right now. The OCP RMC, the Open Edge RMC specification is out. There's a new chassis specification that's been posted that basically brings a 2U Open Edge chassis into the design specs. And then also applying and out for voting now are the two contributions from WeWin, the EP100 S1, which is an Open Edge design server, and then very well timed to coincide with our changing of the Open Edge subproject to the Edge subproject. This is the WeWin ES200 platform. This was presented I think 2 months ago, and is now before the IC for voting. And it is still a 19-inch server, short depth form factor, but it is not Open Edge in its form, in its design. So very much look forward to seeing these voted on and hopefully approved. In the meantime, if you have any sort of feedback that you'd like to provide back to either WeWin or Nokia on the designs, please feel free to do so. That's why we have them, posted out for review. And so with that, that was about all I wanted to cover from the open edge, or from the from my point of view. Before I turn it over to Howie for his presentation, however, are there any other topics that anyone would like to bring up? Okay. And with that, let me see, Howie, how I can get this over to you as presenter.
Okay.
Hold on 1 second.
I am curious, by the way, as you do that, around, like you'll note in my presentation, I have it listed as telco and edge. So like within the telco group, is there any kind of definition, or is it just?
Well, that's I guess that's one, as far as the definition of the telco group, that's a good topic to bring up. The telco charter was recently rewritten, and I believe it was approved by the IC. It's either that or it's out for voting right now. There was always a charter. It was approved, but the documentation, the paper trail that it was actually approved, that couldn't really be found. And plus, every once in a while, it's good to go back and update a charter and make it a little more, relevant to the present. And so that was recently done. And then the charter for Edge was also, recently changed, but really only to, make it the Edge focused sub project instead of Open Edge.
Okay.
Okay.
All right.
Great, Howie. Well, let's
So
see what you got.
Yeah, thank you. Can everybody see my screen okay?
Yeah, it looks fine. If you could go into a full screen mode, it might be, or maybe it's just the way I have it formatted. No, please go right ahead, Howie.
Yeah, hang on a minute. Let me try to get used to the different formatting here. Let me collapse this and then do screen mode. Let's try that. Is that better?
Yeah, well, that looks great.
Okay, perfect. Thanks, everybody. So I am very fortunate that I have been selected to present actually in 2 different categories for Tech Week. So one is here in the Edge group, and a number of you already know us from our Open Edge proposal to do the battery backup for the the Open Edge airframe system, and have had lots of conversations with a number of you around that. And I'm also fortunate that I will be covering some bases in the rack and power track as well, in a few other areas, because essentially what is happening now is that we're seeing new generations of systems, both in the hyperscale data center, and there's a lot of new solutions out there in the edge and the far edge realms. And the major piece that we're finding is a change from some of the more classic architectures, is that especially in, let's say, 5G and edge, and we'll obviously be focusing on that today, we have a much wider deployment and a much wider number of systems. So if, let's say, a cell tower base station right now covers, let's say 10,000 people, you may need 5 or 10 5G modules to be able to support that same number of clients. And what it means is that you now have to distribute your power architectures out there much more significantly in the field. And we're looking at these small cell type of applications, and we're seeing a number of proposals, a lot of conversations with different customers from the major telco hardware providers such as the Ericssons and the Nokias of the world, as well as some of their traditional power supply vendors and some of the companies that are making the radio antennas. So it's been pretty interesting over the last year, year and a half, just seeing some of the different applications and ideas and concepts. And what I'm trying to do here is kind of bring it up from the perspective that batteries are expensive and take a long time to develop. So if 5G needs to be deployed rapidly, essentially the industry is going to be looking for ideally off-the-shelf type of products. But the reality is there's a lot of definitions that still have to occur to even get close to that. So really the basis of this presentation is just to bring up a lot of the considerations that are involved to doing the backup for 5G systems. It's not essentially going to tell you all, this is a solution. It's more about, okay, so when we think about the designs, here are the considerations that we have to cover for a battery. And I will provide some ideas of what do we see as probably the best options. And one of the things I'll also note that I am not an expert on the terminology at all within a lot of the telco systems. I know Mike's got a much better grasp on that, so I'll probably be like leaning on him or anybody else who wants to help me kind of figure out some of the terminology, make sure that we're square. But I do know that radio access network is what RAN stands for there, and what I'm going to kind of go through are some of the different pieces that are in that solution and what backup is required. So y'all can kind of read through this, and essentially it's about supporting the power system in a very wide variety of applications, wide variety of temperatures, altitudes. Every different type of environment is where we may need to have some type of battery backup for the power supply. And I think where 5G becomes kind of critical, probably more than anything else, is in some of these instances where if we think about autonomous driving, where you have a compute node that is working at a very, very high speed, and if the power goes out, there's a lot of trouble that can happen if there's not some type of backup to make sure that system works seamlessly. So I kind of think about that corner case to say that's kind of where we may need to build to in certain instances. So these are the top level considerations for a battery backup for a 5G RAN system. So we're really going to touch into then overall design parameters, which encompass power levels, the environmental that we're putting the battery into, and the system life requirements. And we'll talk a little bit about scalability and system integration and how the different pieces within the whole power solution and the radio network need to communicate and how they are going to physically interconnect. Each one of these pieces is crucial to the deployment and the reliability. And then we'll talk a little bit about the safety considerations and the agency testing that has come into play in a much more specific way over the last 2 years, really getting to the safety of lithium-ion batteries. And then, of course, NEBS is always part of the consideration for the design. So any questions so far? Go. Okay. So as mentioned, we have a pretty wide variety of applications. And if we think about things that are telephone pole mounted or the picture above on top of a rooftop in a metro environment, it could be in the middle of a cornfield, a lot of different places that you may be putting these systems. So most of the telecom systems out there are minus 48 volts. So that's pretty common, but we still do have 12 volt datacom solutions that are out there as part of the overall package. So really we're looking at 48 volt and 12 volt. And then we have power ranges, thinking about each module. And by the way, I'm going to show you a couple of pictures of those a little bit later on to give kind of an idea. So you're really running anywhere from 200 watts to 3 kilowatts per battery module. And there is a little bit of a limitation into how much energy we're going to put in a box, sometimes limited by OSHA, for example. So we may not be able to do much more than 50 pounds per module for anybody who's going to be installing this up in a tower or a telephone pole or whatever it may be. And then we get into runtime because, and this is kind of a key topic in our world, the power versus energy. So when we talk about a power application, it means that we're essentially supporting a short time run, but we have to assume that the battery has to assume the full power load of the system. Meaning that if you have a number of radios and antennas running and it's drawing 6 kilowatts, I need to be able to provide 6 kilowatts instantaneously at that 48 volts to run for a period of time. Now, if we talk about, say, a UPS type of application, sometimes we're looking at maybe 5 minutes of runtime just before the generator might kick in. Or in a scenario where the customer may say, all right, well, we're going to shut down this tower because we're in battery time for a little bit too long now. So you may only need 5, 7, 8, 10 minutes to do that. In other instances, we're looking at an energy application where maybe it's a less developed nation, or it's in an area where the power is inconsistent, and you may say, hey, I'm probably going to have to run this system on battery for a couple of hours every day. So then what you're looking at is an energy application and a cycle life type of application. And you're gonna, in our case, have different cells to support that type of energy application versus power. So it's kind of an important piece within the integral design.
Hey, Hal.
Yes.
Along with applications like that, where your batteries are intended to last a little longer as far as recharging those batteries, yep, after discharge,
yes,
do you see maybe supplementing that with any sort of like alternative energy like solar, or do you typically just plan to charge off of source power when it's restored?
Well, it's a great point. And actually, I have one of the slides in here that points to a possible solar type of scenario. So, and that's what I kind of get to, is that every installation is going to be a little bit different. So, you can essentially put it out there in a super remote area with a solar panel and go ahead and charge from that. So it's really, it could be a hybrid solution. You could have both AC power available and solar for backup. It could be a variety. So either one. But what ends up happening, Mike, and this is what's kind of crucial on our side, is you typically have either power cells or energy cells, and then you have some that are in between that are called mid-rate. So depends on what this application is, and you have to decide up front, well, which cells am I going to use? And it's cost differentials between them. And just like I said, an important piece of trying to even come up with something that's relatively standardized. So we found that mid-rate ends up kind of coming in pretty well these days, so that you can support a pretty high power discharge for the initial inrush, but then you can also have a module that can last a half an hour, 40 minutes. And then what I'll show you as well is you do have the ability of running multiple battery modules in parallel. So essentially each one of those parallel additions adds more runtime. So that's part of your system build out, is the modularity. So the other piece that we go into is environmental. So we have to really look at wide temperature, and assuming that the product itself has to be pretty universal. You can't say, all right, well, this is good for extreme temperatures, and this one's good for normal temperatures, at least in like a radio access outdoor antenna application. So typically you're putting heater units in, and you're also choosing cells that have a pretty wide temperature range capability before they have to be shut off. So, what you're doing with the heater is essentially monitoring it all the time within the case, and then you're going to draw from the AC power to essentially keep the battery pack from getting too low so that it can't actually discharge. And the obvious ones has to be waterproof, 100% humidity capable, earthquake and lightning proof, and then also be able to run appropriately at very high altitudes. So these are all things that when you're dealing with batteries that are in a stationary data center where it's extremely well controlled in the environment, this becomes a different animal as to how to build out these particular battery projects.
You also have to consider how I guess the chemical design of the battery in terms of safe disposal. I mean, I know there are a lot of regulations.
Yeah.
Some areas lead others. Like I know Europe is very keen on making sure that designs nowadays take recycling and disposal into consideration.
Yeah, absolutely. Yeah, and fortunately, there are a number of companies out there that are doing a good job with the recycling of the product, and the lithium ion and the chemistries that are being used in most of the newer types are doing a better job of using some of the less environmentally challenged materials. So, far less cobalt, for example, using more aluminum and magnesium, other naturally occurring type of minerals in there. So the other piece here is system life, that we're putting these batteries in pretty remote applications. So the real key to them, especially with a wider deployment of quantity, is reduction of maintenance. So compared to a steel lead acid, you really want to have a product that can sit there out in the field, will communicate back with the network to let you know, well, what's going on? What's my state of health? What's my state of charge? Have I been, put into battery discharge mode a lot of times? Just give me a general idea of what's happening. So in that case, what we also do is we'll look at LFP, or lithium iron phosphate types. We'll go into that a little bit, which gives a much higher cycle life in general. They're designed more for like 3,000 or 4,000 charge discharge cycles in some of those areas where we have much more unreliable grid power. If we have more reliable grid power, we can use an NMC or NCA type that packs more energy into that same space, but doesn't necessarily give as long of a cycle life requirement. So we talk a little bit about scalability and system integration. And the main point I'm looking at in a number of these different applications is the ability of kind of like, your own regular batteries you're used to using, AA's, AAA, C's. Essentially, you start with one to support a certain load and that you can add more as needed. So as I mentioned, if say your radio tower starts getting built out a little bit more, you have more population in that area, you may say, well, that 30 minutes of runtime isn't enough. I really need to have 60, or I'm supporting a higher power load, so I need to add another battery. It should be really easy to just plug and play. And that's really the key of what you're kind of looking at. So in that, you're going to need to have the interconnect has to be common between all of your different modules. So we're talking about the rectifiers, you're talking about any type of PDUs and the batteries. So everything in there has to have the same interconnect solution, otherwise you're going to run across some challenges. And because you're running power through them, you have to make sure that all of the connectors and all the cabling are going to be able to support those power loads. Otherwise, you're going to have failures or damage. Other important pieces, you have to have that common communication link where we see RS485. It's a pretty solid bet. In this case, CAN bus is another one. So you need to be able to send that information back to the network so nobody has to go out and look for a set of LEDs to understand, well, what's going on with the battery. That kind of defeats the purpose. So some of the safety considerations that have really come online, and I'm kind of like a preacher about this, is UL 1973 and IEC 62619. And really what's most important about these two certifications is that of the containment of any type of single cell failure without propagating to adjacent cells. So the testing goes in such a way that basically you short circuit a cell and it has a thermal event, and essentially the battery pack needs to be able to contain that without going into any type of massive failure to hurt anybody or turning it into a much larger event. It's an expensive test. It's about $75,000 to $125,000 to do that. So it really needs to be baked into the initial design to start with. And as I'm noting here, lithium iron phosphate has an easier ability to pass these tests because the cell itself is the much lower energy density, and the way the chemistry works is it's less prone to having a thermal event. It still can if you abuse it, but it's just less likely. So what we're seeing is that essentially any pack or system that's designed for North America is going to steer towards a UL 1973, and anything that's EMEA focused is going to steer towards IEC 62619. But they're pretty similar tests. And the reason I bring this up with certifications and the cost is that every time you do a different configuration, so you might have a box that, let's say it's 2 kilowatts. If you have one that's 12 volt and one that's 48 volt, well, those are two different systems. Each one's going to require that certification. If you have one that's 1 kilowatt and one that's 2 kilowatt for the same 48 volts, depending on how you design it, you may be able to only have to pass that test once and then have that test be relative to both power levels. So these are things that we have to have figured out on the front end. And what we've seen is that even some of the existing vendors who are doing battery backups for radio towers today have had to come out with new product lines just to be able to support meeting these certifications. And just the scoop on the internals, and I'll show you a picture of that in a minute, means that you have to add gaps between the cells, and you may have to add material in between the cells to achieve this certification. So you have to redesign your pack to meet these certifications. And then of course NEBS, which has a very long history in safe and reliable electronics. Any questions before I move on? Okay. So I'm going to show you a couple of pictures here just to give you a little bit of context and also talk about some of the other applications that we see within the systems. So most of the presentation I've covered so far is really kind of relative to these next two slides, showing you some of the pictures as more of the outdoor oriented solutions to support the radio towers. Most of them we're seeing a 48 volt. Most of them are unregulated output because we're pretty much assuming that it's tied in with the rectifier. So depending on how you do your power architecture, you could run the battery power back through the regulated portion of the rectifiers, or depending on your loads, they may be able to support a wide variety, a wider input, really from about 40 to 58 volts on the input type. We already talked about this difference between lithium iron phosphate or lithium ion. The NMC stands for nickel manganese cobalt, and NCA is nickel cobalt aluminum. So those cells are a little bit higher in energy density, and what we're seeing in that world, frankly, are some of the newer cells that have been designed for the automotive environment. So that's, anybody can ping me for whatever level of detail ad nauseum that you'd like. But essentially, these are the two different chemistries that we're seeing as pretty valid for these applications. And power levels we're seeing in these modular solutions are 250 watts to 2.5 kilowatts. And as I mentioned, because of OSHA requirements of being one product less than 50 pounds, pretty much the best density I can stuff in there is about 2.5 kilowatts of power. So that's kind of what we're looking at. I mean, you can certainly make it heavier and put more in there, but in general, we want to make it so that the line worker doesn't have to have a second person or any type of mechanical assistance to be able to get that up into the installation. And when I mentioned hybrid loading from power to energy, we talked about that a little bit earlier, where essentially you have an inrush current to take over the power from the AC rectifiers to the full load, and then depending on how the system is set up to essentially identify and say, oh, we've gone to battery power, so now we might end up transitioning away from this load, or you're going to determine, all right, well, now I'm going to get into maybe a slightly minimized mode of power consumption, and run for, you know, whatever it is, half an hour, hour, 2 hours, depending on how many battery packs you have in the system. All right, and the other two items we've already covered. So I want to show you a little bit of an idea too of what the inside might look like. I guess in some ways, you know, it's kind of like Lego. All right, I have an array of cells in there, and what you'll see is a larger gap between them than in packs of old, where you used to just stack your cells just all right next to each other and glue them together. But now we're looking at gaps of typically 5 to 6 millimeters in between. So we have to have cell holders to keep them all in place. And because each one of these cells is roughly 70 grams, we also have a decent amount of mass that we have to contend with, plus we have to do the termination of each one of these cells. So we're looking at, you know, anywhere from 80 to 160 cells that we have to terminate and put in the pack. And the yellow plates there are the heaters that we'll put in. And then as you can see, some O-ring sealing, and then the green is a PC board assembly that go in there. One of the other things, and this is partially because I came from the connector industry, I get kind of into the weeds and the details around that. But, you know, one of the things is, you know, these are not inexpensive batteries. And if you put a cheap connector on it and the connector fails, you now have an expensive paperweight. And, you know, it's one of those areas of don't cheap out in the connector because it will affect the whole system. You know, clearly we need them to be IP67 rated, and I assume that somebody's putting them up on a tower wearing gloves, it's cold, and it really needs to be just very, very easy to make the connection. And also, you know, one of the pictures, if I go back up, you'll see that there are legs. So even if somebody were to put this down on the ground, they're not going to hit the connectors and potentially damage them. All right. So you can kind of think, let's say this battery pack could be anywhere between $500 and $1,000 each. So, you know, for say a $10 connector, you don't want to damage the whole battery pack and say it's unusable because you damage the connector. So you put a little care around the design.
And how refresh my memory on IP67. That is, well, it's dust and water intrusion, right? So it's completely sealed in terms of dust, and the 7 indicates that it can,
I think you can go a meter below water.
Yeah, I thought it meant submersible. Yeah, okay.
Yeah. And, you know, I think in some instances you might say that's overkill, but I don't know. I mean, I think all of us have been through some hurricanes and deluges that it's almost as if you're underwater. And it's possible. I mean, you know, it's just, you never know where somebody's going to install this. So, right. You know, our feeling is IP67 at a minimum. And trust me, all the shake and bake from NEBs and the altitude, there's a lot of work on the mechanical side of doing this type of product. So now we go back indoors to something a little bit safer and a little bit easier from the mechanical design. And this is something most of you guys have already seen. So this is the airframe open edge backup solution, and a little bit easier to kind of work with compared to the outdoor environment scenario. But, you know, still it's going to be an important part of the overall solution. So as we talk about some of these IoT type of applications that maybe doesn't have a big radio antenna, but maybe this is inside of a factory or inside of a campus, and it's still supporting a lot of high-speed data. You know, this is an important piece that may be just sitting in between the AC power going out and a generator kicking in, or a much larger scale UPS supporting the system. Could be anything, but, you know, we're pretty much figuring this is going to be in more of those far edge type of applications for the open edge airframe solution. The other thing that we're seeing, especially in the telco space, is a larger battery backup type of solution. And this is where, you know, this product starts to phase over to the rack and power type of discussions, where if we look at a telecom rack versus a datacom rack, frankly, from a battery backup perspective, the only real difference was the voltage. whereas the telco, it's been pretty traditionally in 48 volt, and the datacom's been more than 12 volt. But they're even starting to convert over to 48 volt as well. So if you think about some of the standard cabinets that are out there that may be filled with steel lead acid type of solutions, that with edge and far edge applications, they're saying, well, I don't have that much space to work with anymore. And now I also have less weight that I can handle, because maybe this is in, a metro application and I have a floor of an office building. So I can't put all those steel lead acid batteries in there, and also it's going to be remotely monitored. So this is where the lithium ion solution starts coming in with a value proposition. So, we just have a wide variety of applications here. So I'm not going to go into too much detail, but this is something that shows a picture, frankly, of what we already do for a 48 volt single phase UPS battery solution. And it's available up to 5U heights with different chemistries available. And what we're also seeing, interestingly enough, from a couple of companies are saying, well, I'm really not yet ready to jump over to lithium ion. So what do you have in between? So we've been involved with a couple of design discussions around some of the nickel-based solutions, which some say, well, that's older technology, nickel metal hydride or nickel zinc. But at the same time, it does give better energy density and more modularity than steel lead acid, but it just doesn't give that same energy density as you can get with lithium ion. So just different options that are out there. And again, parallel stackable, hot swappable, et cetera, same safety certifications. And then Mike, as you had asked about solar, now this particular project we're building for a company, and it goes underneath the solar panel. It's a residential and small commercial application. But as we were thinking about it and thinking about edge and far edge solutions, that there's no reason why you wouldn't potentially be able to put the solar powered panel out there to support both your radio and your processing equipment. And these are designed to have much larger numbers of cycles. So a 3.5 K cycle or 10 years of operation. So these are good possibilities. And these ones are either using lithium iron phosphate, or there are new lithium ion chemistries that are designed for solar that are just designed to do a very high cycle life. So interesting possibility.
So Howie, that's basically once a day, right?
Yeah.
That 3.5. Okay. Wow.
Yeah. That's what you're figuring.
And that's full discharge.
Yes.
Once a day, every day for 10 years.
Correct.
Wow. Okay.
Yeah. Yep. So, that's kind of where the industry's gone. And fortunately, there's a number of cells out there that are able to support it. And, it's heavily based on these two applications. It's solar and automotive. So they were all been pushing the cell manufacturers to get much longer cycle life.
Huh.
Yeah, a lot of good options there. So to wrap up, I want to just give you guys a couple of links to take a look at, some good papers out there, both from our friends from Nokia and Ericsson and CommScope, and a little bit if you want to geek out on some of the battery technology from Inventus Power, but some good reads going through and seeing where a lot of these applications are going to fall. And like I said, if I was to kind of wrap it up to say, oh, I've got one product to fit them all, the answer is nope. I don't. So I think it's something where, as the industry starts deploying more and more, we'll see some more commonality between what those systems start to look like. And then, we're hoping that we'll be able to develop some products that become easy to scale, build them in block modules so that, we're able to deploy product very quickly to truly meet the need of the market. So, and there you go, my call to action slide. And yeah, any discussions or questions, comments, feedback? I do appreciate the feedback because this is what I'm submitting. And if you guys, have ideas of how to change, update, adjust, shrink, because I think I'm given 15 minutes, so that's why I was also talking pretty fast.
Yeah, I think that was right around 20, 24 minutes, I think is what it was total.
Okay.
So, yeah,
shrinking.
No, that's some really interesting information, Howie. I do appreciate it. Yeah, it's a side of edge deployments. There's all the environmentals and the form factor and the power concerns, but this very much plays in toward the availability concerns, and and especially when you bring up something like driverless cars, the 6.9s, 5.9s, 6.9s types of availability is going to apply just as much to the edge as it does to the telco data center.
Yeah, it really does. It really does. I mean, and even in an automated IoT application in a factory, so if you have a high-speed process going on and the power blips, and you're relying on that information from sensors being processed, again, it's a crucial little piece, because otherwise, basically, if power goes out, then the whole mechanism comes to a stop instantaneously.
Right. Yeah, absolutely.
Yeah. So that's how we think. So thank you everybody for listening in and your time. And again, any feedback that you guys have, please send to me.
All right. Yeah. Thank you, Howie. Appreciate you taking the time to present this to us.
Absolutely. All right. Let me figure out how to undo myself now.
Okay. And with that, I'll throw it open to the floor, ask if there's anybody else that has any other topics or items that they'd like to bring up for this call.
Hello?
Yes, please.
Yes, yes, I have a quick question for the previous battery part. For the 5G, normally, the power consumption on the cell side around 2 or 3 times more than what LTE is consuming. So for this battery, this presentation, will that consider, this time 2 or 3 times more than what LTE is consuming?
Howie, that was for you.
Yeah. Can you maybe rephrase that? Because
Oh yeah, the thing is for a 4G, and then for the cell side, normally the power consumption is around 1/2 or 1/3 of what 5G is going to consume. So in that case, if you consider the time, right, for the battery part, so for 5G it will be only 1/2 or maybe 1/3 of the yeah. So in your design, have you ever considered that part for the time or the energy that's going to be charged to your battery, those type of things?
Yeah, absolutely. And that's kind of where I was getting at for the different size power modules that are required. I mean, so discussions I've had really range from 200 to 2.5 kilowatts of power out of one module. So,
but Howie, it looked like your modules were, I mean, they were modular, so it looks like they're almost they're stackable in a way, or you could run them in parallel to give you increased
That's
endurance.
That's exactly it. So what you basically would do is determine the size of your module and probably come up with something, and this is kind of key. If you have physical space to work with, but you're trying to also deal with different power levels and different cost levels, what you can do is consolidate with one mechanical design that's going to be consistent throughout the whole family. And then each one would have a different power level, which basically means, either fewer or more cells on the inside of it. All right. Okay. Because what that would allow you to do is pay for the tooling for only one physical housing, and they use the same interconnect between all the different ones. And then you basically just have different amounts of cells on the inside of that module. I mean, you could do a couple of different sizes. It just depends on what your budget is. But what I'm getting at is that every time you do a major change in the size or voltage and you have a different product, then you have a different agency certification that you have to go through for each one of those modules. And that's where it starts to get really expensive.
So it's kind of to your advantage to create more of a building block type of deployment, right? Where you just go through a certification once.
Right, so the recommendation would be pick your voltage, pick your mechanical housing, and then have different power levels coming out of that same exact housing. And then we may be able to reduce the number of agency certifications required. Because all we're going to be doing on the inside of that module is adding parallel strings of cells. So the safety certification, the battery management solution, everything on the inside of the pack is pretty identical. The only thing that's different is how many cells am I putting inside the box.
Okay. Yeah, the thing is like here is like if you put too many, well, I'm not a battery or power expert, but the thing is from my intuition is like if you put too many batteries or cells within one compacted frame, it may cause the safety concern. So,
well, yeah, you have a safety concern from, it's not as much how many cells I put in there, as long as I'm using the appropriate cells that are going to be able to pass certification, but it's also that I have to have an appropriate gap between the cells.
okay.
All right, so I mean, if you're thinking clean sheet design, then my gap between the cells is going to be exactly the same, whether I have 40 cells in there or 160. So the gap stays the same, but my battery management system stays the same. All right.
Okay.
And what you can do in your installation then is just decide each time that you go to deploy, well, how much power and how much runtime do I need, and just how many batteries do I need to plug in? It's as simple as that.
Okay, sure. Thank you. By the way, are you going to publish the slides?
Yes. As soon as I have these in my final revision. Yeah.
Okay, sure.
Yeah, just get them to me, Howie, if you want to post them before the tech days, and I'll get them up on the Edge wiki.
Yeah, I will. I'll let you know this week, because basically once I submit them on Friday, that's pretty much it, Mike. So it might be it might be a tweak based on what I presented today. I'll probably take out 1 or 2 slides to shorten it down to that 15 minutes.
Actually, as far as putting it on the wiki goes, it's really kind of unrelated to the, to the tech days. So if you want to keep that additional information in there,
okay.
I only see that as a good thing.
All right, then I'd say, yeah, go ahead. You can run with it probably as it is.
Okay. All right. Thanks, Howie. Okay.
Absolutely.
Anything else from anybody else? And if not, with that, I'll thank you all for joining. Have a great day, great rest of the week, and look forward to seeing you all at the tech days next month.
Thanks,
Have a good day.
Thank you. Have a good day.
Thanks, Mike. Take care.
Bye.
Thank you. Thank you.
Thanks. Mike.
Bye.
Thank you.
Bye.